Good afternoon. Sorry. It should be the last topic. Thank you for still being here. I hope probably for the topic, not for the barbecue. I'm glad to stand here to share some experience about Adobe Flash Player, in which we got a lot of interesting discoveries 1 or 2 years ago. Although Flash Player will retire from the stage, but currently there are still APT attacks which use Flash 0 days emptied in Office files. In addition, the ideas in ActionScript may be used in other ECME script implementations, like V8 of Chrome, Chakla of Edge, SpiderMonkey of Firefox, and so on. I will introduce an exploit which was a candidate of Pontoon 2017 and a new and a general exploit technique. So if you are interested in this stuff, this topic is for you. There are 2 main parts in our topic. The first part is Flash vulnerability discovery. The second part is Flash vulnerability exploitation. We are researchers from Palo Alto Networks. Before we introduce our work, let me show you a person in the martial arts first. There's a Kung Fu legend who can use his one hand to attack and the other hand to defense. He can practice attack and defense by himself. Seemingly, we use our right hand to do the offensive things like exploit, vulnerability discovery, mitigation bypass, something like that, and use our left hand to do some defensive things like anti-exploit, vulnerability detection and mitigation, and so on. We will spend 1 slide to talk about the background. Flash has been a hot target for attackers for many years because it is supported in multiple platforms and very exploit-friendly. However, from 2015, Adobe released multiple mitigations like vector cookie check, ByteArray cookie check, isolated heap, system heap, memory protector, something like that. Especially the anti-use after free mitigations like isolated heap and a memory protector are making use after free vulnerabilities difficult to exploit. In the first chapter, we will introduce how we use EF3 implicit reflection to fuzz Flash from designation to implementation. Before we start, let's consider a philosophy question. Theism believing there's God and the God made everything, including the universe. But pantheism believing the God contains the universe. From the universe Big Bang theory, the universe is expanding. Seemingly, there are 2 main ECME script fuzzing strategies: outside generator and inside evolution. In outside generator strategy, testing case generator is like God. It generates testing case and runs them. In inside evolution strategy, there's only one self-evolving testing case. It can run many times and keep evolving. Each strategy has proved to be effective, and we choose inside evolution strategy. Now we come to see how we construct a self-evolving testing case with the help of reflection. Reflection is the ability to examine, introspect, and modify its own structure and behavior at runtime. That is to say, we can simply use string, hello string, instead of call hello method here. ActionScript 2 has implemented the similar reflection with AS Native. In general, AS Native returns a function reference. It's like all the ActionScript2 functions are stored in a spreadsheet, and you can access them by rows and columns with AS Native. The AS Native is very friendly and is very friendly for fuzzing. You can set the first and second argument here. You can set the first argument and the second argument of AS Native randomly and call AS2 functions. In the right side, you can see the first line, AS Native 500 represent the getPen method of sound class. But AS3 is not that easy. AS3 has two important methods which can use for reflection. The first one is describe type in Flash UTLS class. The second one is get definition in application domain class. If we call a trace describe spread, we can get a huge XML file. And this XML contains everything about the input class. We can see there's extend class and method name, method return type, and parameters counts of method and parameters type and parameters property, and accessor name, accessor property, read and write, and accessor type. All of the information we have. So we can use this information in XML to instance class, get property list and a method list, even with a filter, and then access the property and call method randomly. You can see here, where's my mouse? You can see here, we get the property randomly and access property. Here, we got a method randomly and call this method. Do we need to implement all of interfaces by ourselves? The answer is no. There are open source projects which implement them and we can call it directly. For example, you only need to supply the class name and you can instance this class. And you only need to supply class name and method name, you can call this method. Similarly, you only need to supply a method class, a class name and an instance name, and you can access this field. After we know how AS3 reflection work, we come to see how to make a self-evolving testing case. The idea is very simple. We choose classes randomly, instance them, set fields randomly, and call method randomly, and loop the whole process. There are 3 layers in our implementation. The first layer is for some basic libraries, like reflect library, random generator, something like that. The second layer is for method, field, constructor interface called by template directly. The third layer is for main, loop body, template. We will introduce them respectively. At the very beginning, we need to specify all of classes' names which we would like to fuzz. We find them in Adobe official page, and here is a package name, and here is a class's name. We wrote a script to parse them, and there are some statistics on the left. We can see the number of each class type, and the total number is 2,000 892. It's a huge number. On the right side, it's an example of TV SDK type. We find a lot of vulnerabilities in this type of class. Global class is for storing some global variables. For example, instance dictionary stores all of the instance of classes, and method return dictionary stores all of the value of get method, and field return dictionary stores every return value of get field. To be mentioned here, we randomly add these types to set array type. Set array type, which we will traverse in each set methods and set or get fields. It will help construct a complicated and evolving testing case. Constructor class is not very complicated. It firstly calls get constant, which we'll introduce later, and then generate valid parameters. After that, call new instance. At last, push return values to global variables. The similar pattern for get class fields and set class fields. The difference is that there's a type confusion flag and an integer overflow flag in set class fields. If we set class type, if we set type confusion flag, we will not choose the right type for parameters. If we set an integer flag, we will face some potential integer overflow integers like FFFF to int and uint parameters. Also, the similar pattern for set class method. Here, we not only type confuse parameters, but also confuse methods from different classes. That's why you see in the parameters, there's set method 2 and class type 2. Now we come to talk about how to generate valid parameters. The first important part is getting valid constants. For example, in load with background manifest method, there's the second parameter container type must be HLS. If not, this vulnerability will not be triggered. So to increase the code coverage, we traversed all of constants in a package and pick the valid for parameters. Here's an example of constants in Flash media package. You can see here it's HLS, and there are 147 packages which contains valid constants totally. The second important part in generate valid parameters is mutations. We use this strategy to get the right parameter for the constructor, set field, and set method. If type confusion flag on, we return random value without type match. If not, we randomly choose a value with type match. We will check specific dictionary, basic type dictionary, instance dictionary, method return dictionary, field return dictionary. If all of checking is failed, we will generate the required type and instance a new class for the parameter. The objective of generating valid parameters is making the testing case complicated. Here is an example of vulnerability we discovered. At the bottom, you can see the resolve method, the parameters of resolve method is random and a little bit complicated. Here's new, this this is a method return. This is a new class. Here is an example of template. We choose classes first, do some initialization, and call get and set field and set methods. We can use this single template to find many CVEs. Here, I only list some of them, not totally, not the total number. Now we will use one slide to talk about sanitization. Flash use managed heap and unmanaged heap as heap allocators. We redirected unmanaged heap to system heap and return on the page heap to make memory corruption in unmanaged heap easier to detect. We redirected fix alloc here, fix alloc and out of line alloc to heap alloc. And we redirect free, fix alloc free, and out of line free to heap free. Reproduce. We hooked trace function to write logs to a file. We firstly find the trace address in a text file generated by our internal tool here. You can see R2 generated all of the native functions of Flash, and we find a trace, the address of him, and we hook him. And redirect trace function to our trace check function, in which we only deal with the call which has only one string argument. For example, we call trace seed in AF3 layer, and we got the seed number in the log file. We used a Mason twister to reproduce crash samples. It only needs one seed and can generate a group of fixed random numbers. When crash happens, the log seed will be used to generate all of samples, all of the same random numbers, and the crash sample can be reproduced. We use this fuzzing system to find over 50 AF3 vulnerabilities and got 23 CV numbers in several months. Here is an example of simple but exploitable vulnerability found by our fuzzing system. The setObject method expects an object type here. The setObject method expect object type parameter, but if we give it an integer or a number type, it will crash. We can see the EEX is 0C0C0C00, and we can we input the 1A, 1E, 1E, 0, and we can control the EX is 0C0C, 0C00. It is likely to exploit. The other case study is an interesting DoABC opcode type confusion bug found by our upgraded DoABC opcode fuzzing. Previous DoABC opcode fuzzing used exist samples on the internet. Our upgraded DoABC opcode, the previous DoABC opcode fuzzing heavily rely on what samples were downloaded. Our upgraded DoABC opcode fuzzing using samples we generate by ourselves. We log every AF3 codes by hooking trace function, and we compile Flash samples from these AF3 codes. Here is a screenshot of AF3 codes which generated by hooking trace function. You can see the codes can be compiled directly. There are some method call and set parameters, something like that. We randomly modify the DOIC opcode and got this vulnerability. Here is a crash information. And we can see the EDX is 11807900. It's also likely to exploit. Now we finished the first important part, finding Flash vulnerabilities with reflection. I will introduce the exploitation part in the left slides, especially for the undisclosed but exploit-friendly HashTable object. This use-out-free vulnerability we found in early 2016 and patched when patching the other two vulnerabilities in November 2017. We can see the EIP has been set to an invalid value in crash information. We can see if we do some backtrace, we can see the EIP is from call EEX, and EEX is from ECX, and ECX is a string object. Oh. Yeah, it's a string object. It's a use-out-free vulnerability. In the next slides, we will introduce the root cause and introduce the important AF3 codes one by one. The first important AF3 code is new media player item event. It will generate two objects in the memory. It will generate two objects. One is script object. The other is media player item event. You can see there's a pointer in script object pointing to media player item event. The second important AF3 code is get object. It did two important things. First, it make a copy of script object. Pay attention, the content of script object is the same with the previous one, but the address is different. It's a new copy. And call set that item to set a script object into media player item event here. It sets the 2-4 offset in media player item event with a script object. The third important AF3 code is the second get object. It also did two important things. Firstly, it get the cache. It get the script object cache from media player item event here, and then return directly. Pay attention here. It should return object type 29F8CE9, but return number type 29F8CE8. And then it store this wrongly script object into atom address in atom write barrier function in JIT. These slides will see what happened. The atom address and the script object are managed by GC heap and added to GC stack here. Here in the GC stack, when garbage collection triggered, that means the ZCT reap function will scan GC stack and call reap object on atom address. On atom address and script object. Eventually, the script object ref count will decrease twice to 0 and freed. Yep, this is you can see the same address CE9 before it's a script object. After it is occupied by string object. That's the root cause of this use after free vulnerability. This use after free vulnerability lived for over 1 year and was patched when patching the other two vulnerabilities in November 2017. We analyze the patch. We can see the patched object here. The patched object return the right object type. After it get the object and or EX with 1, return the object type. But do you think it's a good patch? The patch will bring some potential issues. I will leave this question for you. Maybe you can find another 0-day in this same function. After knowing the root cause, we come to see the exploitation. The exploit in X86 is not very hard. You can split ByteArray to heap layout in first step and convert script object use after free to string use after free and use string use after free to get a read primitive leak. For example, you can leak the ByteArray cookie and then trigger the use after free again and reclaim the memory with fine constructed string, and then use medium player item even.type to get the write primitive. You can get a huge size ByteArray by writing ByteArray length and length cookie. At last, you can get the capability of read and write the whole process memory, bypass mitigations, and execute your shellcode. Today, I will not talk about the 32-bit exploitation. You can try it by yourself if you are interested. Exploitation on 64-bit is difficult. There are two reasons. The first one is string object memory structure is different. You can see the green color. Where's my mouse? You can see the 4 bytes of green color is string type. It is for NSI, Unicode buffer type, and the 4 bytes with red color is string length. After we clean this memory with other objects, the string type is the high 4 bytes of a pointer. You see, it's a pointer. It is not controllable. And this time it is 16B, and another time is a different value. So if you want to use string to do the info leak, it may cause crash. That's the first difficulty. The other difficulty is Spring on x64 is not that easy. Using string to leak all of objects we need is almost impossible without heap layout. To bypass all of difficulties mentioned before, it's time to introduce HashTable object. We will introduce why it's a new exploit-friendly object and how it helps us bypass all of difficulties and complete a whole exploit chain with only one use-after-free vulnerability on Windows x64. Simply speaking, HashTable is a type of object in AF3 which store key and value pairs. The value can be changed without changing the HashTable memory structure. The memory size of HashTable can also be controlled by the count of key and value pairs. Here's an example of HashTable. You can see here the red color is the first element. 444406 is a key of the first element, and this pointer is a value of first element. It is a pointer to ByteArray, and you can change this object dynamically without the whole HashTable memory structure change. It's a perfect exploit-friendly object. The elements are highly controllable. You can change HashTable value without memory structure change. Most importantly, it is in the same isolated heap with almost all of AF3 objects. So we can get a stable read primitive with string and HashTable. And HashTable can help us read any object without Spring. It's a very powerful capability in x64 platform. Now we will introduce the exploit process one step by step. The first step is heap grooming. In this step, we leave a slot to make the vulnerable script object in this slot. We leave a slot here. The second step is converting script object use-after-free to string use-after-free. Firstly, we insert the vulnerable script object into the slot. And then we trigger script object use-after-free again. The memory is freed, but in the AF3 layer, there's still a reference. And then we clean the memory with string. And the string here, and in the AF3 layer, there are two objects, both have the reference to the same memory. And at last, we free script object in AF3. We freed script object in AF3, and now in AF3 layer, the string object is reference this memory, but the memory here is freed. So you have a string use-after-free vulnerability. The third step is a very important step. Firstly, we freed all of strings allocated in heap grooming. Here, you can see all of the heap block in this page is available. And then we free the whole page and reclaim the memory with HashTable. You can see the HashTable size and the string size is different. The HashTable size is 118, and the original string size is 28. And in the AI3 layer, there are both two objects, string and HashTable, reference the same memory. The content of this memory is HashTable. In the process of reclaiming the memory with different size HashTable, there are some possibilities. Because the string size is 28 and the HashTable size is 118, so the string address can be 7 possible addresses in HashTable. To make the string type wholly controllable, there are only 2 possibilities which can be successful. Here, every line is a 2A size, so the string only can be these 7 positions, but only string is in the first line or third line with red smile face. It can be successful because we can control string type here. And the string buffer is the HashTable value. We can change this HashTable value dynamically, and we use string to read any object here. So the successful rate is 2/7. Here are 2 puzzles for you. Why the size of HashTable we construct is 118? Can we improve 2/7 success rate? Because I don't have time to introduce all of details here today, I leave these 2 puzzles for you. In step 4, we can use string length to check if HashTable reclaim is successful. If the length is 19998E and 199B6, it means HashTable reclaim is successful here. If these 2 values. Once success, we begin to use string and HashTable to leak information. If failed, we run the exploit again. Now we can use string and HashTable to do the info leak. Firstly, we leak the address of memory. Here is ByteArray. We can read memory address from the offset 88 here. We read memory address, firstly. And we reset HashTable value to HashTable object, and we read HashTable address from the offset 20. Here is HashTable object address. You can see it point to here. And we reset HashTable value to QName. It is QName. And we can read the address of QName, local name, and QName URI from the offset 20 and 28. We reset HashTable value to vector, and we can read the address of vector buffer from the 300 offset of vector object. Now we leaked all of addresses of object we need, and we can fake object in vector buffer. And now we faked object in vector buffer to construct the data that write primitive need. You don't need to care about the details here unless you debug this exploit, but You just need to know this data is for making the function path go to write instruction. And this data is for preventing crash after write primitive. And this function is for setting the address and value of write primitive. Step 6, we trigger the UAF again and reclaim the memory with string here with string, and we set the vector buffer leaked before in string buffer, and we faked the whole object in the vector buffer here. You can see we write some address here and fix some value here. In step 7, we call media playing item even type to do the first writing. Firstly, let's see why media player item even dot type can write any value to any address. Media player item even dot type can call GC weak reference and get function and eventually write our control value to our control address because we fixed the whole object. Okay, you can see at the beginning, we control the input object. This is a vector. This is a vector address we faked the whole object, and we control the function pass to here, and we make this check true, and we enter these instructions. At the last one, you can see this is any value we controlled. This is any address we control. So we can use this instruction to write any value to any address. And we use that write primitive to write HashTable value with memory buffer. Here is a memory buffer, and we read the cookie. That is what we want. We read the cookie in memory from the offset 288. And you can see I have a screenshot of from browser. We get the cookie. It's the same with the memory. After we have ByteArray cookie, we will do the second write and the third write primitive to write mbuffer with memory address and set mbuffer cookie. And eventually, we have a God mode ByteArray which can read and write anywhere in x64 platform. Here, you can see we leaked the table of memory here. So the whole process is a little bit complicated. Let's summarize. Firstly, we do heap grooming. Second step, we convert script object use after free to string use after free, and then we reclaim the memory with bigger size HashTable. And step 4, we use string and a HashTable to leak the address of array, QName, and vector, all of the objects we need. And we fix object in vector buffer. And then in step 6, we trigger the use after free again with find constructor string. In step 7, we use string and media playing item event type to write hash table value with memory address. And in the step 8, we leak the content of memory, including the memory cookie. In step 9, we use string and a immediately item event type to override and buffer with memory address and set memory cookie. Eventually, in step 10, we get a God mode ByteArray which can read and write anywhere in x64. In step 11 and 12, we bypass CFG by overriding the return address leaked in function object, and we call load library JavaScript in shellcode. Today I will not introduce the last two steps because it's a universal method. Before showing the demo, I will spend 2 slides to discuss why it's a general exploit technique. Firstly, string and hash table can generally provide a stable and a powerful read primitive which can read any object in AF3. Here, you can see in AF3 layer, there are 2 objects, string and hash table, both reference the same memory. The memory content is hash table. We can set any object as hash table value and use string to read the content of any object. It's a very powerful and useful capability of InfoLeak. And secondly, we use string and object attribute can generally provide a stable and a powerful write primitive which can write any value to any address. You can see in AS3 layer, there are string and object both reference the string, the same memory. The memory content is string. We faked object in vector buffer located in string buffer, and we can call object attribute to write any value to any address. In addition, we can see hash table is in partition 0 in the GC alloc memory structure. You can see here it is in partition 0. So it is not isolated. Almost all other AS3 objects like string, script object, dictionary, something like that, almost all use default partition 0. And so it can make other use-out-free vulnerabilities which is considered to unexploitable before to be easier to exploit in x64 platform. So eventually it's time to demo. Actually, this exploit work from Flash 19 to Flash 27. I tested on Flash 24 in Edge, Windows 10, x64, 1803 with the latest patch. And in shellcode, I just call a load library JavaScript because JavaScript is a JavaScript engine in IE8. So if we find JavaScript.dll in Edge render process, that means our shellcode executes successfully. To be mentioned here, why our shellcode just use load library JavaScript? I will tell you a story. Around 2 years ago, Microsoft disabled to pop-up calculator in Edge render process, but you still can pop up other applications like Notepad in a demo. In that time, someone said to Microsoft guys, Disable calculator is useless. Can you disable everything? But 1 year later, that joke came true. Windows 10 Anniversary Edition turned on child process policy, and you can't create child process in Edge renderer process anymore. I have to say, you win, Microsoft. I have to use Process Explorer to show JavaScript has been loaded into Edge render process in my demo, but I still miss the calculator. So let's see the demo. Oops. And you can see we use 24 Flash version, and the system is install the latest patch. And yeah, it should success. Let's check. See, I use a dead loop in shellcode to make it easier to find which process is exploited. And you can see in that process, CPU is very high, and it is dead loop in shellcode. And let's check the JavaScript. You can see JavaScript is loading into this memory. That means our shellcode is exploited successfully. And you can see it is in Flash 24 version. Okay. Where's my mouse? Summary. At last, we come to summarize the whole topic. We mainly introduce two parts. One is fuzzing, and the other is exploit. In fuzzing part, we introduced how we implement an AF3-based fuzzing tool with random instantiations of new objects, random invocations of method, and random fields getter and setter using the implicit reflection in AF3. And in exploit part, we showed how our HashTable object attribute and a string break the anti-use after free mitigations and generally supply read and write primitive for use after free vulnerabilities. We can mitigate this type of exploitation by isolating all of exploit-friendly objects like HashTable, string, array, something like that. We can also detect this type of exploitation by monitoring the abnormal ByteArray. So that's it. Thank you for listening. Thanks, Recon.
Thanks for the nice talk. What I'm curious about is how you bypass the memGC protection with HashTable.
Bypass what?
memGC. There's another protection, which is called memGC. If there's any references pointing to the heap or stack, the user after free is not triggered at all.
Yeah, we maybe in Flash. I don't. I'm not understand the mitigation you mentioned. Maybe. Oh, memory protector.
Yes,
oh yeah. Because in partition 0, I think there's because it is managed by managed heap. It is not memory protector. Yeah, in managed heap. I can show you. Oh, here. I think in managed heap, because it is managed by GC garbage collection, it is not memory protector. It don't have memory protector in this heap allocator.
Okay, thanks.
So then, thank the speaker again.
Thank you.